Hi, my name is Anna Liu, and this is my lab report for lab number 4, which is analyzing a spring mass system that is oscillating in an arc. First, I used Tracker to gather the observed positional data. Then, I used GlowScript to create a computational model to obtain the predicted positional data. And then finally, I compared the two data sets to determine the proficiency of the computational model and to see whether or not the total energy was truly conserved in the system. And spoiler alert, it was. Here are the equations that were used in the lab. First, we have Newton's second law, which shows how the system's change in momentum is proportional to net force. Then we have the energy principle, which shows how the change in energy of a system is dependent on the surrounding work and the thermal energy exchanged. Next, we have the velocity update and the position update formulas, which were derived from Newton's second law. I also used the gravitational force, spring force, potential gravitational energy, and potential spring energy equations in this lab, and they will be shown later in the code. Next, I collected my observational data through the usage of Tracker, and you can see my results depicted to the right. I only used frames 7 through 105 because that is when the hand is no longer applying a force to the system, and the system is therefore isolated. And for initial conditions, the mass was 0.402 kilograms, and the length between the mass and the top of the spring was 0.7 meters. And then I also listed my initial position, which was obtained by the first data point I collected through Tracker. And finally, I set my initial velocity to 0 as the mass was released from rest. I then calculated the constants that would be used in my GlowScript code to create the computational model. T stands for the time it takes for one complete oscillation, which I calculated by averaging the first 3 oscillation periods. Then using my T, I was able to calculate for K, which is equal to spring stiffness. And then I solved for the approximate relaxed length of my spring using the K and the spring and gravitational force formulas. And this was able to be done because I knew that the net force in the y direction was equal to 0. Next, I plugged all of those constants and my initial conditions into my GlowScript code as seen below. I then created formulas to solve for L, which is the current length of the spring, L hat, which is the direction of the spring force, and S, which is the compression amount or stretched amount of the spring. And then I coded formulas to solve for the system energies, which would have been the potential spring force energy, the potential gravitational force energy, and also the total energy in the system, which is just the sum of the potential spring force energy and the potential gravitational force energy, which you can see here. Finally, I decoded for my while loop for the computational model. First, I set my T range to be the length of time that my predicted data ran for, and then I coded the computer to solve for the total net force acting on the mass, which was done by adding together the spring force and the gravitational force. I then used the momentum principle to update the position and velocity of the mass at every delta t. And then finally, I updated the spring conditions, which you can see at the very bottom. My next step was to calculate the changes in energy for the system. This was done by first solving for the new kinetic energy of the system, the new potential gravitational energy, and then the new potential spring energy in the system. I then used those values to find the change in energy of the system by subtracting them from their old values and then adding them all together. And finally, I updated my time for my while loop, which is seen right here. And then ultimately, I was able to compare my observed and predicted data points to each other through GlowScript. And as you can see, although my data is semi-similar for both of the data sets, it's not overall very accurate. And you can see as time goes on, the computational model actually becomes less accurate. And this lack of similarities between my two data sets could be due to one of two main reasons, the first being human error. As I hand track the position of the mass myself through Tracker, there's a large margin for error as I cannot accurately determine the center of mass at every single frame. And the second error could be that the computational model treated this system as being completely isolated, while in real life there could have been work done on the system by the surroundings that I was unaware of. And then we have the what does it mean? Was the energy principle satisfied? As you can see in the graph created from my computational model, yes, it was. This is because the orange line, which indicates the change in energy of the system, remained at 0 throughout the entirety of the time. And this is because there should have been no external forces acting on the system, so the work done by the surroundings and the thermal energy transferred from the surroundings to the system should have been 0. And then for the very last slide, what does it mean? Compare the two oscillation periods. For this, I just repeated the same methods I used to calculate my t and k in the x direction, but instead I used the y direction this time. And as you can see, depending on which direction you choose, there will be slight deviations in the computational model. And this is yet another source of error in the experiment for the validity of the computational model. Thank you for listening.